salt tectonics and at the regional and local scale. And Rodolfo also has 10 years experience in the oil and gas industry, 2 years as a mud logger, and 8 years in exploration and development. So we are excited to listen to his talk today. For you who are joining us throughout the talk, feel free to post your questions in the question and answer session, and we'll get to that after the talk. Rodolfo will be happy to answer your questions. And so, Rodolfo, I pass it on to you now.
Okay. Thank you, Ova, for your presentation. I will share screen now. So, okay, are you? Okay. So thank you for your invitation. I will be presenting here the preliminary results of my PhD, which deals with the salt tectonics of the offshore Tarfaya Basin from a regional to a local scale perspective. My PhD is carried out in the Institut de Recerca Geomodels in the University of Barcelona, and this work was done with data provided by Repsol. My supervisors are Julio Ferrer, Josep Anton Muñoz, and Gonzalo Zamora. So basically, with what I will show you in this presentation is the talk layout is about going from a large scale, a margin scale along the Moroccan margin to a local scale, to the mini basin scale in the Tarfaya Basin. And in this trip that we will be doing, we will be discussing first the early stage breakup evolution of the Central Atlantic and its impact on salt tectonics. Then we will focus on the Tarfaya Basin, that is on the southern border of the Moroccan salt basin. And we will discuss the salt tectonics in the Tarfaya Basin. And in the end, I will show you the preliminary results of the final stage of my PhD, which is dealing with the salt sediment interaction in the Cenozoic of the Tarfaya Basin at a mini basin scale, as I said. So let's start. This margin scale phase of my work was guided by Shanreto Manachal and Mark Rowan, and it's the result of a 2-month stay I did in the University of Strasbourg. Also, Leonardo Pichel is also collaborating in this part of my PhD. So the main drivers of this part of my work is to characterize the crustal domains on the Moroccan passive margin, to see in which of the known classification of magma rich versus magma poor margins that exist does this Moroccan salt basin fit, and what is the fitting with the conjugate margin of Nova Scotia in Canada. Also, which is the role of inheritance and along-strike variations along the passive margin, which is the timing of rifting, hyperextension, breakup events along this margin, and what is the impact of all these events on the salt tectonics, structural styles that we see, and how did they control them. So first of all, the Moroccan passive margin evolution starts in the late Permian with the extensional reactivation of the Variscan structures that we can see here oriented in the northeast to southwest direction. So during Triassic times, rifting continued and propagated from east to west and from south to north. And by late Triassic to early Jurassic times, salt was deposited along the margin. As we can see in the map, different accommodation zones bound different basins along this passive margin. For example, we have the Tarfaya Basin in the south, the Agadir Basin northwards, Essaouira Basin, Safi Basin, etc. So what we can see here is that mainly all the salt basin along Morocco is developed on what is known as a non-volcanic margin or a magma poor margin, whereas the Tarfaya Basin is located in a transitional domain between a volcanic and non-volcanic. And we see that no salt is deposited in what is classified as a volcanic margin in the zone here in offshore Bushdur. So we see that the salt basin in the Moroccan passive margin is bounded to the west by this magnetic anomaly called the S1 magnetic anomaly, which is thought to represent the continent-ocean boundary. So what we have here is a salt basin developed over thin continental crust. This is very important. So during Toarcian times, initial oceanic spreading took place, and the sediments corresponding to the prograding shelf were deposited during the Jurassic. In the early Cretaceous, an erosional conformity is recorded, and this erosional conformity eroded a great part of the Jurassic shelf, and the prograding sediments of the Tantan Delta were deposited on top. This Tantan Delta is mainly developed on the southern region of the Moroccan salt basin. Then during late Cretaceous time, the initial conversions between Africa and Eurasia took place, and this caused thick skin inversion and the record of an erosional event, which is the base tertiary unconformity or base Xenospheric unconformity. That caused the erosion of the proximal shelf and the resulting sediments from the uplifting of the high Atlas and all these the reactivated orogens bypassed the shelf and were deposited deep offshore. We see here that this map is taken from Tari, and he classified the Moroccan salt basins in distinct provinces. He sees the diapirs labeled in number 1 and depicted in yellow here, diapir, saltworks, and turtle structures. And in 2, he sees in this polygon here, he describes rafts and isolated diapirs. Whereas in 3 and 4, alloctonous salt bodies are described. So this is important because we see here the distribution of the primary structures that were not laterally translated along the basin. So this will be important for some of the topics that we will discuss later. So the main objective of my work was to first define the crustal domains. What I mean by crustal domains is the unthinned continental crust, necking zone, thin continental crust, exhumed mantle, if there is exhumed mantle, and the oceanic domain. Okay, so I did that following integrating different types of data. Here we see the magnetic anomaly map of the area, where we can see the S1 magnetic anomaly here, right here. We see also the free air gravity anomaly map with the main depocenters clearly depicted and some of the inverted structures here. We see how these basins are getting shallower to the south, where salt is not deposited. And I use also reflection lines, regional reflection lines here in black, and one very important refraction line that is here near Safi, that it's depicted in red. And of course, I also consulted the other works published. For example, this depth to the Moho map done by Fulea, inverting mainly gravity data. So this is the refraction and reflection seismic data set. I put it in a map with the fitting between Nova Scotia and Morocco. This map is from Loudon and others, from 2012, and this is my main map where I put all the information that I used for mapping the crustal domain. So the main objective of this work was to define the crustal domain and their aerial distribution, the stratigraphic framework, define the stratigraphic framework from the seismic interpretation on both margins. How do they change along strike, and how do salt structures change also along strike, along both margins? So what we can see here is that my main line, the mirror one line, the reflection line, and its corresponding reflection line, the S1 on the Nova Scotia side. All these green lines here are the Nova Scotia profiles used for this study, the reflection profiles. And the white lines are the reflection lines used on the Moroccan side. This is the fitting that I obtained when comparing the two reflection lines, the smart one and the mirror one. The fitting is quite good, and there are some quite the definition of the crustal domains can be clearly established. Mainly in the Moroccan side, we have an unthin continental crust, a necking zone that is marked by this shallowing of the mohawk here, a thin continental crust domain, and an oceanic crust domain marked also by the S1 anomaly. And this corresponds also with the Freer gravity anomaly maps and the magnetic anomaly map that we obtained along this transect. In the Nova Scotia side, we also define clearly an unthin and a necking and a thin domain, and we see here a somewhat problematic domain with high increase in seismic velocities, the sudden increase, which could be interpreted according to the authors Funk and others as a transitional or exhumed mantle domain, and then a clear oceanic domain. So by doing this and following this pairing, the next step is to do a conceptual restoration fitting of both margins. So what I mean by this is take out the domains, the different domains, and see how they fit together. It is not meant to be a proper restoration, of course, but it was carried out to see if we were comparing things that make sense, and they actually do. From what we can see here, the domains, when we take out the oceanic transitional thing and we only put together the necking domain, we can see a pseudo restoration of the conjugate margins at the post-necking phase. And when we do that, but taking only the transitional and oceanic domains and leave only the thin domain, we see that they also fit very well. So the idea is to start thinking about what if salt is deposited at this stage, and what if it's deposited at this stage. What would be the expected differences in structural styles and salt tectonic evolution? That is the main driver of this part of my thesis. So after that, I mapped these domains with all the information I gathered on the Moroccan side, and I defined an oceanic domain, a distal oceanic domain, a thin domain in green here, and a necking zone or domain here in brown. All these domains were, of course, bounded by these accommodation zones that they already mentioned, and defined the different basins that we have along the Moroccan margin. We have the Tarfaya Basin, Agadir Basin, Essaouira Basin, and Safi Basin, basins mainly, which are the objective of this work. After doing this and putting on top the interpretation done by Tari and others, it is interesting to see that this red zone here, this red polygon, which is describing diapir, saltworks, and turtle structures, meaning primary structures which were not translated. It's better developed on the south in the thin domain, whereas going north, we can see that it starts being involved in the necking zone here. Okay, this is just putting one map on top of the defined crustal domains. We have a part here onshore Essaouira with salt that is somewhat problematic, but I won't I won't get into this right now. So let's go on. When we compare the seismic reflection data on both sides, on both conjugate margins, we can see some similarities in structural styles. For example, going from south to north, south is on below, and on top we are going north. We see that the main salt features developed on both margins, on the southern Nova Scotia and the Tantan transect here. The salt structures are developed on the thin continental crust and are developed mainly in a trough here, no? In a narrow trough where salt is actively growing at the distal edge of the basin, whereas it has been already secondary welded and it's buried in the more proximal region. The same thing occurs on the Nova Scotia side. This is quite similar on both sides. When we move north, in the Agadir Basin, this is corresponding to the Agadir Basin here, the transect 364, and the transect 1400 is in central Nova Scotia. We see that we have less salt in the Nova Scotia side, and we see a different structural style in the Agadir Basin. We don't see the actively growing structures only occurring at the distal edge basin. We see that the actively growing structures are occurring also proximally here, and we have some salt that is being deposited on a quite thickened continental crust here. And as we go north, this is further enhanced, and we see that in the northern Morocco, we see some salt rollers and salt deposited in the necking zone, as previously described by Tari in his map. We see some rafts here and some gravitational salt tectonics taking place in this portion here in this proximal domain. And on the Nova Scotia side, we see the same, exactly the same, but very similar structures are defined in the Nova Scotia side. So this is summarized here in this interpretation, where I also put the crustal domains in it. So we see that salt is mainly developed on the south in the thin continental crust with this salt style that I already described. We have some salts going up deep to the necking zone in the Agadir Basin as we go north, and in the Safi Basin, in the northernmost portion of the study area, we see that salt is being deposited clearly in the necking domain, as well as it is the same as in Nova Scotia northern portion. So I am only showing this line to you because I think it's quite impressive, and because it's one of the main lines that was kindly provided by Steve Lawrence, and it was really helpful to tie all the interpretations along strike in the Moroccan margin. And in this line, it's an along strike line, but anyway, we can clearly describe the different crustal domains that we have already mentioned in reflection seismic, but here are clearly depicted. A thin continental domain here in the Agadir Basin, a continental ocean boundary here in this place, matching the S1 anomaly, and the oceanic domain is clearly depicted here. So what is the idea and the model that we are thinking of here? So if we consider that a synchronous deposition of salt along the margin, the Moroccan margin, and we think about a propagating system, rifting and oceanic spreading center that is going from south to north, then what we would have is that salt is being deposited on the southern Moroccan salt basin, or meaning the Tarfaya Basin. It is being deposited mostly on the thin domain, whereas as we go north, this salt is being located in the necking zone. It is advancing up deep in that necking domain. We are thinking this model is based on the classification made by Mark Rowan in 2014, which defines and classifies salt as being deposited in seam thinning or seam exhumation or seam stretching. So we would have a seam thinning salt in Tarfaya Basin, which we will see later on, and seam necking to seam thinning salt going north to the Safi Basin. This is the main idea behind this part of my work, and that would fit also with the observations made on Nova Scotia, on the Nova Scotia side, where we have also more refraction data acquired. So this is all, of course, based on the stages during the development of a magma poor margin. Here clearly illustrated and modified by Perron-Pin, Vidic, and Marshall, and Perez and Gousignier. So putting all these things together, the classification of Rowan and the classification of magma poor margins, and thinking about the propagation system propagating to the north, we can put all these things together and think about how this affects our salt basin, or putting it in another scheme. This would be more a very simple evolutionary model, thinking about accommodation zones, delimiting different basins, and propagating system to the north. If we deposit salt during the synchronous deposition of salt, but in different tectonic settings, we would have different salt structural styles as we go from south to north along the margin. That is the main idea behind this simple drawing that I took and modified from Uranga here. So this is the end of my first part of my presentation. Now we are going to zoom in and start talking about the salt tectonics in the Tarfaya Basin. Hopefully, a paper will be submitted soon about this, and the collaborators in these papers were my supervisors and Mark Rowan. So I won't get much into detail here because I already talked a lot about the tectonic setting of the basin. What I want to emphasize here is that we will be focusing on the southern limit of the Moroccan Salt Basin. That is where the Tarfaya Basin is located. And the geological history and evolution, it's the same as I already described. So the main research drivers here are two: describe the structural styles and along margin variations, and evaluate which are the main controlling factors on the salt basin evolution. This is the main focus of this talk. So what we see here is my data set. Here in red we see the 3D seismic cube, and in the other lines are 2D seismic lines, and these are the transects that I constructed. So we see here a structural map from the top of the acoustic basement. Very important feature here is the Capsule horst, that is this paleo high that we see here, that it's constraining the thickness of salt to the east in the Tarfaya Basin. The salt is mainly deposited in what I call the Proto-Atlantic Depot Center, and we saw all the salt structures in black are constrained mainly in this depot center. And the other boundary of the basin, the western boundary of the basin, is clearly marked by the S1 magnetic anomaly, which is thought to represent the ocean continent boundary. And to the south, we have these accommodation zones that prolongate to Fuerteventura Island. Here we have some Mesozoic outcrops of normal oceanic crust in Fuerteventura, and they match these faults which trend in the northwest-southeast direction. And to the south, we have, as already explained, a magma-rich margin. So we have that the limit of salt is marked by a transition from a non-volcanic or magma-poor margin to a magma-rich margin to the south. Taking a look at this central line, this is the A line. This is the main line in the Tarfaya Basin that we will see. We see here some of the already described structures. This is the Capsule horst, which is clearly controlling the thickness of salt to the east. We have the exhumed mantle, which is interpreted as exhumed mantle in the western boundary. And we have that the main salt structures are all developed within the Proto-Atlantic Depot Center. We have proximally, we have these salt sheets with counter-regionally dipping stems and secondary welded stems. We have expulsion rollovers, as we see in the Jurassic and in the Cretaceous. We have a thick Cretaceous succession marking the progradation of the Tantan Delta, which is clearly observed here as clinoforms. And we see that going distally, we see that we find these actively growing structures that are currently deforming the seabed, no? And that are still actively growing, are not secondary welded. Okay, this is the big picture. One of the main features here is, of course, the base Cenozoic unconformity that we see here in brown. And we see that the Cenozoic mini basins are mainly developed on the distal margin of the basin, whereas the Cenozoic sediments overlap the shelf to the east. In a strike image, what I want you to show you here is that this is the Proto-Atlantic Depot Center, and we have the distal salt basin limit marked by the exhumed mantle and and oceanic crust domain. And to the south, we see that the salt basin ends in these accommodation zones or basement heights that are interpreted in seismic data, with some intrusives taking place as well. So this is another deep oriented line that is south from line A. And we see here, what we see here is a narrower basin, and here one of the most conspicuous features here and most important features here is the Capsule Anticline. This is an important anticline because it discovered oil in the 80s or 70s from Jurassic carbonates. And we define this structure as a salt core anticline bounded to the east by this expulsion rollover that was later on it was reactivated by thick skin inversion. This reactivation faults the base Cenozoic unconformity and makes some provokes some unlapping of Oligocene strata against the unconformity. We also see the counter-regionally deep welded, secondary welded stems in a proximal domain and a distal salt sheet deforming the seabed, as we did in the previous deep oriented section. And going north in another deep oriented section, we see that the thick skin inversion that we described previously is clearly depicted here. And we see that we find a salt detached linked system here with up deep extension and a close down deep contraction that is decoupled from the formation occurring in the deeper levels in the basement, which is affected by thick skin contraction. This thick skin contraction is also folding the base Cenozoic unconformity, and we find this Oligocene strata unlapping on this unconformity, as we did observe in the previous section. Also, as in the previous section, we find all these proximal salt structures dipping landward or with counter-regionally dipping stems, secondary welded, and buried by the BCU, the base Cenozoic unconformity. And on the distal margin of the basin, a salt structure actively deforming the seabed, as we already described. All these depositors that are migrating in general basinwards. When we describe the depositors migration trajectories, we see that they are almost all of them have a basinward migration. When we see the maps, it's quite interesting to observe that when we classify the salt structures, we see that the salt structures buried at the base tertiary unconformity are here depicted in black, whereas the active salt structures are clearly classified, in purple in this map from the thickness map from the Jurassic. When we classify the structures according with their dipping or not dipping stem, we see here that the salt structures with counter-regional stems, which are depicted in white here, are somehow matching the thickest deposition of lower Cretaceous sediments. These lower Cretaceous sediments correspond to the prograding Tantan Delta. We could see that these counter-regional stems are matching these white structures, proximal white structures, whereas the salt structures with vertical stems are mostly located basinwards. When we see a thickness map of the Cenozoic with the active salt structures depicted in actively growing salt structures depicted in purple and the salt structures buried at the BTU in black, we see that the mini basins, the main mini basins in the Cenozoic are developed distally. So we see that all these mini basins are actively subsiding nowadays and are the main drivers of salt diaperism distally. This is clearly observed in this thickness map from the Cenozoic. I carried out a structural restoration of this of line A. I will summarize the main results here. This restoration was carried out following a methodology proposed by Rowan in his paper in 1993, which considers isostatic compensation, decompaction, and thermal subsidence, as well as change in water depth. The main results here is that I restored 4 stages: top salt, top Jurassic, top Cretaceous, and the present time of course. And the main results here is that in the salt was deposited in a wedge-shaped basin with its maximum thickness on the distal margin of the basin, which corresponds to an exhumed mantle domain, according to my interpretation, with a maximum salt thickness of 2 kilometers, a maximum water depth of 2.5 kilometers, and a topsoil slope angle of 1.3 degrees. We see that during Jurassic times, early primary welding occurred in the proximal setting, and the prograding shelf, firstly siliciclastic and then carbonatic sediments generated this or provided the sediments for these early many basins to start allokinetic growth of salt. And during the Cretaceous, we observed that the base Cretaceous unconformity and the prograding sediments of the Tantan Delta that further enhanced the counter-regionally dipping stems and promoted the salt sheet extrusion from Barremian times. And these counter-regionally dipping stems give place to nearly vertical stems on the most distal margin. All this, of course, this original salt deposition was controlled by the paleotopographic high, which is the Capsule Horst. Okay. So to see it in a 3D view from the south, we could say that the Tarfaya Basin was developed on a narrow magma-poor rifty margin over thin continental crust. The southern limit is marked by a volcanic margin or a magma-rich margin, and the Capsule Horst marks its eastern limit, and the salt basin was deposited following a wedge-shaped geometry with its maximum thickness on the distal domain. From early to middle Jurassic times, the progradation and loading exerted by the shelf progradation during the initial passive margin stage probably triggered early salt withdrawal, and thermal subsidence, even though it has an impact in tilting the basin, did not lead to gravity gliding, because we don't see evidences of early gravity gliding in this basin, probably due to the narrow characteristics of the salt deposition that we have here. During the early Cretaceous, the progradation of the Tantan Delta contributed to the basinward expulsion of salt, developing seaward leaning diapirs on the paleoslope of the prograding sediment wedge, and the most distal structures were developed with nearly vertical stems. From Barremian times, salt sheet emplacement took place in the proximal domain. And during the late Cretaceous, starting from the late Cretaceous and during the Cenozoic, shortening led to thick skin inversion, erosion, and rejuvenation of salt structures, with the proximal structures being secondary welded, whereas the distal structures continue to actively growing nowadays, even deforming the modern seabed. Okay. So in the end, I will show you just a couple of slides of the last part of my PhD, which deals with the salt sediment interaction in the Cenozoic of the Tarfaya Basin. So I worked in a small portion of the seismic cube. Here I focused on this rectangle here. I have this A line which I restored, so I have this area is quite well understood. And The main drivers for this part of my PhD was the 3D interpretation of the salt structures, 3D seismic attribute calculation, mainly amplitude and frequency attributes, to characterize the seismic geomorphology in the Cenozoic, and together with the definition of allokinetic sequences, if possible. So we see clearly here an horizon, intramiocene horizon slice with the RMS attribute, and we see that this turbiditic channel lobe system is confined within these two actively growing diapirs during the Miocene. We see another horizon slice taken in the Mayo-Pliocene. It's again an RMS amplitude attribute, and here I put the line AA as a reference. This is the mother line of my work, which I restored, and we see here this rectangle marks the area where this attribute was extracted. So what we can see is again these diapirs and also the most distal ones are restricting the location of this feature, of this sedimentary feature, this channel. In fact, it's an accumulation of channels. It's a vertical stacking of different channels. It's not just one. And we can see here, for example, some slumped units on the side of this diapir here. And also here, we have an interference between slumps and channels occurring at the same time. This corresponds with a part of the seismic where we observe a wedge here in this part of the section. This is line BB, and this channel stacking is related clearly to this wedge sequence. Now this is going distally in the same area, but distally we see these mass transport deposits that are clearly observed here in the transect. We see that we have a fold and thrust system generated here in the most distal domain of this slump, as defined by Scarselli in his book. And we can clearly observe a basal shear surface, and we can also observe in this spectral decomposition color blending the longitudinal shear zones that are separating different domains in this body. So we have different tectonic domains with different velocities separated by these longitudinal shear zones. And finally, this is a spectral decomposition of the sediment of the sediments corresponding to the Pliocene to recent strata. These are horizon slides of spectral decomposition column blending of horizon slides in the Pliocene recent succession, where we can see sediment waves, multiple large sediment waves oriented southwest northeast, with some waves rotating near salt, as we see here and as we see here. These near salt wave constructions are influenced by the positive salt seafloor expression, as described in this work by Dunlap and others from 2013, where he describes very similar features in the Essaouira Basin offshore Essaouira. In this case, they describe these features in the Aptian succession. So that's all for me. Thank you very much for your attention and for inviting me. Hope you enjoyed it. I'm open to any questions you may have.
Great, thank you, Rodolfo. Really nice presentation. So if
Thank
you
you.
have any questions, please drop them in the chat or the Q&A box, and I will try and keep tabs of the questions. Oh, there's already one question in the chat, actually. So I guess we'll just start with that. Kick off straight away. So this one is from John Philbrick. And he's asking, do you observe mass transport complexes in the Tarfaya like what is seen in the Azores Basin, brackets Cenomanian in age?
No, in fact, this work, particularly the last I showed you from Dunlap, describes several mass transport deposits in the Cenomanian and Upper Cretaceous, which are not observed in Tarfaya. I think that the vicinity of Essaouira to the active High Atlas uplift may be responsible for finding these mass transports deposited in Essaouira and not finding them in this southern portion of the Moroccan Salt Basin.
Okay. So I was going to ask a question. I was just thinking of the kind of depositional model that you made for the salt and how that relates to the architecture of the oceanic and continental crust.
Yeah.
Are you interpreting that the salt on both sides of the margins in your first part of your presentation, so is deposited as a single salt body across both sides?
Yeah.
Because I was just thinking of, like, for example, with the conjugate margins of Angola and Brazil, where they're actually deposited in different sub-basins that may or may not have had some level of connectivity, but it seemed like in yours you're suggesting this was a singular deposition.
Absolutely. This is a simplification. This is a model to try to explain mainly what is happening in the deep offshore region of both basins, but we have some things to take a look at. For example, what happens in Essaouira. In onshore Essaouira Basin, we find that the salt is seen stretching according to this classification from Rowan. So what does it mean? Is it a different salt? Is the same salt, but this was deposited in a different phase? Is salt diachronous? So what I did here was maybe an oversimplification, but it's the starting point to start addressing the other factors that are not quite fitting in this model. So, but absolutely, we have, for example, in the Nova Scotia side, we have salt being deposited on the proximal part in a place called the Yarmouth Arch, and they find that it's a different salt, that it's Permian in age. So yeah, it's quite, it's more complicated than this. But I think that if we only consider the distal domain, the thin continental crust domain on both margins, I think this salt should be the same, and we don't have timing constraints to be certain about the diachronicity of this salt. But regarding seismic interpretation, we could say that we don't see any evidences that allow us to interpret it as being diachronous along the margin.
Yeah, okay, thank you.
Welcome.
And Mark's asking what the evidence is for being deposited in sub-basins for the South Atlantic. I guess that is an ongoing debate. I shouldn't have said it like this is a known thing, but there is a review paper that I cited in my thesis that pointed at different sub-basins to do with different compositions of the salt and that. But yeah, this is not a known thing, even in that area, no. Many who would disagree, yeah, sure. So we have some more questions in the Q&A. Scott Kruger says, excellent talk. I always wanted to look more closely at the conjugate margin to Nova Scotia, where I worked. There you go, thank you, Scott.
Thank you.
And Scott's also asking, Does the isopack thin around the salt in your earliest isopack, followed by this becoming a thick, suggesting that there was a regional broad salt pillow early that evacuated over time to make the later thicks?
Yeah, well, you see, I mean, when you see the thickness maps here, you see that the major thicknesses in the Jurassic are taking place also in proximal positions and in distal positions. So what I think is that you have an early expulsion of salt in the proximal domain, because you have most of your sediments are coming from the prograding shelf that is marking the initial passive margin setting, and you have expulsion rollovers, and you have anticlines, rollover anticlines, and all these structures in the proximal domain, where you have also the early primary weldings, and you have the most of the sediment accumulation space. Most of the sediment accumulation space is in this position. But not only, you also have some thick Jurassic mini basins taking place in the distal positions of the basin. So salt is being mobilized not only on the proximal domain. It is early primary welded because of its initial well shaped geometry and its initial lower thickness in the proximal setting, but it's continuously being mobilized in the proximal and in the distal setting. I don't know if that answers the question.
Yeah, hopefully, yeah. Great. So we also have a question from Ricardo Pereira. Tari also describes an alternating upper to lower plate at the Sulfone Plateau. Do you see any relation between the plate architecture with any salt distribution and styles? Yeah, I might incorporate that. It's true, because you see that on both margins, the basement structural architecture is quite different on both margins. So Tari relates that to an upper plate or lower plate setting. Yes, it could be. It could be that the original morphology of the margin is due to an asymmetric decoupling between both margins. And he sees southern, from south to north, a transition from an upper plate to a lower plate. So yes, it's completely possible, and I'm not questioning that. I have to test it if I can incorporate it in my work, but it's definitely possible. Okay, thanks. We have another question from John Philbrick asking, what are the implications of counter-regional dipping depot centers and salt stem welds? Okay, so following this, I will put this one. So these counter-regionally dipping welded stems are developed on the paleoslope of the Tantang delta system. So as salt is being expelled basinwards, and we see that clearly in the migration of the deposenters that I depicted here in white. As salt is being expelled basinwards, these salt bodies are progressively being transported basinward as well. We have a differential sediment accumulation rates that it's laterally expelling salt basinward. And in the end, or in Barremian times, the expulsion, the interaction between salt sediment and salt expulsion rates makes that this salt sheet emplacement here from Barremian times and on. So that is the main cause. They are located on the paleoslope. Okay. Next question then. We have a few questions coming in now. I'll try and keep up. So we have a next question from Jonathan Redfern saying, interesting to see the influence of the inherited rift topography on a large scale. Do you think this is also controlled? Do you think this also controlled local depot centers of salt within your salt basins with thicks and thins? Hard to see on the data as it's so deep.
Well, for me, and this is an opinion, it strongly influenced. I'm going to put this one here. For example, in this one, we can see that the thickest part of the Moroccan salt basin is in Essaouira, and it's like clearly it is laterally constrained. So you have these northeast southwest structures that are delimiting different sub-basins, where you can see that the amount of salt is different along the margin. So the structural inheritance in this regard is really it has an impact, a strong impact on the salt accumulation rates during the initial phases of the Moroccan salt basins. And also these accommodation structures influence I think the different subsidence patterns along the margins. So I think that we should start thinking about what is the subsidence if this northern salt was deposited during the necking phase. What is the subsidence during that stage? Does it allow for a vertical stacking of salt that is thicker than on another stage, for example in thinning? So if we analyze the subsidence evolution during the different stages, necking, thinning, and so on, and we could put numbers to that, then we could stack different amounts of salt vertically in that context, different context. So I think it has and all these subsidence patterns could be delimited by these northeast southwest accommodation zones. So I think it's very important, the inheritance in that regard, and also in others, of course, but that is another important matter.
Yeah, for sure. Okay, so we have a question from Ishmael Essabar, who says, first, thank you for the presentation. Recently, ONHYM declared the presence of natural gas reserves in the Tarfaya and Bassin Basin. Could these salt dome structures act as reservoir?
Salt as a reservoir, you mean, or?
You say salt dome structures, so maybe the sediment associated with
okay. Yes, of course. Yes, of course. I mean, in the offshore Tarfaya Basin, in the all that I've shown you in the deep offshore, there's only one well drilled, and it reached only the Cenozoic succession. So the Mesozoic is untested on the deep offshore region. So it of course there are many underexplored or unexplored play types in the Mesozoic and in the Cenozoic as well. We can see that here with the seismic attributes, we can see clearly a turbidite channel that has like 30 kilometers and it has not been drilled. So of course, yes, and it's influenced by salt. So yes.
Yeah, sure. Okay, so then we have a question from Roman Manhaes. How much extended the crust before oceanic spreading, or how much extension reached the lithosphere to exhume the mantle?
That's a great question. So when we see this map here, we see that the thin domain in the south, it's much narrower than going north. So that gives you an idea of how much extension do you have of continental crust in the Agadir Basin, and how much extension do you have in the Tarfaya Basin, just looking at the thin domain. So from this map, I would say we have a lot of extension in the Agadir Basin, whereas we have small amounts of extension in the Tarfaya Basin. Is this related to the transition between a magma pool and a magma rich to the south? Probably. Probably we have that when we are transitioning from one domain to another, we see a decrease in the extensional rates of continental crust. Okay, so yes, definitely we see that variations, and it has its impact also on the structural style of the salt structures we observe.
Yeah, that's a difficult question. I think there's one more question in the Q&A from Jafar Hassanpour. Extensive work and good presentation, Rodolfo.
Great.
Could you elaborate on the paleo sea floor and water depth derived from restoration during the salt deposition? Deposition in 2 kilometers water depth. Yeah,
so water depth was taken following the results of previous work was carried out analyzing the stratigraphy of data from Wenke and others, and WISA. So, of course, as always with this subject, we surely don't have a strong constraint on which was the water depth during the deposition of salt. But I would say that as I went through the structural restoration, the results I obtained in the different stages were coherent. I mean, I didn't have I always have the shelf between 100 and 200 meters in depth. So I consider also the eroded interval from the Upper Cretaceous, and that gave me also the depths were quite coherent. And also I used the published data about water depths that they are what they are. They have there is uncertainty always in this matter, and we have to take into account that most of the data is obtained in the shelf, and we have no water depth data in offshore. So hard data is hard to find in this regard.
Yeah, sure. Okay, I think that is all the questions I can see. Or we have a few comments. Very good talk. Thanks for sharing. Thanks for a nice presentation. Thank you for the great presentation. And then a final comment from Mark, I think. The restoration does not mean water depth. It means depths below global sea level. They could have been brines in partly air-filled holes. There we go. Okay, and then that's it then, I think. Yeah, thank you very much, Rodolfo. Thank you everyone for tuning in. And yeah, if you do have any more questions, you can send them directly to Rodolfo, or you can email the AAPG Salt Basins email, and we'll forward any questions you have as well. Okay.
Great, thank you very much.
Great, thank you everyone. Okay.
Bye.
Bye, have a good day.
Thank you.